Hear from one of the inventors of the LEDs shining all around you right now, in your phones, on the streets, in your homes, next on the K-12 Engineering Education Podcast. I'm Pius Wong in Austin, Texas. My guest is Dr. Russ Dupuis, a recipient of the Queen Elizabeth Prize for Engineering for 2021. The prize recognizes world-altering achievements in engineering, in this case, for the invention of LED technology, or light-emitting diode technology. Dr. Dupuis played a direct role in its development since the 1970s. He spoke online from his home near Georgia Tech. Dr. Russ Dupuis, officially welcome to the K-12 Engineering Education Podcast and the Engineering Word of the Day podcast, where our engineering word of the day is going to be LED. And I understand that you are one of 5 recipients of the 2021 Queen Elizabeth Prize for Engineering. I just wanted to ask you, how does it feel to win the Queen Elizabeth Prize this year?
Well, this is, first of all, a great honor. The fact that the Queen's name is associated with it, and she has, in the past at least, presented those awards, it's a great ceremony, a great honor, and it's the most prestigious prize we have in the world for engineering. And so it's a very great honor to receive it. Also, with my PhD advisor, Professor Nick Holniak, Jr., and a good friend of mine, M. George Crawford, and my 2 friends from Japan that I've known for many years, Shuji Nakamura and Akasaki Sensei, Izamu Akasaki from Japan. They all had critical roles to play in this technology, and I'm fortunate to be included with that important set of researchers and workers, and I feel grateful for this honor.
Yeah, I'm glad you mentioned your co-winners who, you all did a lot of work, and I'm sure there's even many, many more people who are on your teams and everything. And you mentioned that Dr. Holniak, you co-author a lot of papers, you've done some research with him. Do you all hang out, or do you all know each other then, basically?
Well, I was in his research group at Illinois as a graduate student for 3 years. I got my PhD in 3 years from the bachelor's degree. And so I knew him intimately then. And fortunately for me, after I left the University of Illinois with my PhD, a few years after that, more like 10, I suppose, we started to collaborate again on a research problem. So I had a chance to work with him again as an engineer, scientist, when I was working at Rockwell International. And then we also were able to do some things together when I was at the University of Texas at Austin as a professor. But I get back to Illinois at least once a year because that's where my family is from. And I always try to get to Urbana to see Nick. It hasn't worked out well this year and last year because of the COVID. In fact, I was there in Chicago in February of last year, 2019. I saw him then. But I was also back in the era of COVID, February 2020, and I decided not to go to see him because I didn't know if I was carrying it.
Wow.
Early February, I was going to go there, but I said, no, I don't want to even take a chance. So I flew home, and then Georgia Tech shut down the labs on the 13th of March. So we stopped our research then.
Yeah, that's always a topic of conversation with people I'm talking to for this podcast. And are you able to conduct the research the way you normally would these days?
Yes, my lab is back in full operation now. My students are here, my postdocs are here, my engineer is here. So we're functioning. Of course, things tend to be a little slower because just getting orders placed has an extra time constant. Because of the fact that people are not all working in a coordinated space and time. So some things get delayed. Fortunately for us, all of my team has been safe. We haven't had any COVID positives. We get tested every week, once a week. So we're keeping track of this carefully.
Well, that's good to hear because I know that you and your team does a lot of good work. And before I get too deep into COVID, I do want to talk to you about, this great honor that you have won with your co-winners and the technology you helped develop. But just starting out really broadly, could you make a case for why LED technology is so important for all of us, for humanity, why it deserves this kind of recognition?
Well, as you well realize, this technology has evolved now over at least 60 years. My PhD advisor, Professor Holniak, made the first visible LEDs in 1962, basically.
Mm-hmm.
So we've been hard at work on this for a long time. But the fact that LEDs, as we know them today, are so energy efficient and so well designed for the human eye because of our engineering, they've become the dominant source for lighting in many, many parts of our economy. Soon, of course, I think there'll be a big effort to remove all of the fluorescent lighting in the buildings in the United States and replace them with LEDs. But any new construction today, any new building, any new parking garage, any new sports stadium, any new subway station is going to have LED lighting because of the energy efficiency of those products compared to any other light source we know of today. And in fact, Professor Holniak showed by simple physics arguments that the LED is an ultimate lamp. It is the direct conversion, essentially, the direct conversion of electrical current to light with, in a well-designed device, nearly 100% efficiency. So it's remarkable that the technology has moved so well and so fast, really, although 60 years sounds like a long time. But once we got to the point of the performance of more or less 10 years ago, the adoption rate dramatically increased. So most of us recall the days of calculator displays and even watches had red LED displays. So that was a slow curve where people's lives weren't impacted. But I think when they started to appear in traffic signals, people started to recognize that's pretty remarkable. I've taken that heavily engineered, high intensity incandescent bulb that was in the green and red and yellow traffic signals and replaced them with LEDs. And they were bright enough to see in the sun. They were bright enough to see, under all sorts of lighting conditions. I think in many cases, people first recognized how well those devices worked when they saw them in traffic signals.
Do you think that LED tech deserves more recognition as part of helping our environment, that whole movement to reduce energy consumption and all of that?
Well, that's, I hope by now, obvious. I mean, that's one of the elements of the prize being given to the LED workers, the energy efficiency. It's well known that calculations show, at least, that if we had 100% adoption of LEDs in the United States, we would probably need 10 less nuclear power plants. And there'd be many gigatons of carbon dioxide not emitted into the atmosphere from power plants that are using fossil fuels. So this is certainly part of the green energy revolution. It is not only converting our energy sources from renewables, but saving energy in every possible way, and both in terms of high efficiency light emitting diodes and in terms of better power supplies for light emitting diodes, better power supplies for computers. It turns out the same basic material systems that have given us the white LED can also be designed to be an electronic device and become the element in a power supply. which has much more efficiency than silicon, which is currently used today. So I see a day when not only will our energy solution be lighting comes from LEDs, but that our power electronics have shifted from silicon to the new materials that we use in LEDs for electronic circuits, for power at least.
Solar cells or batteries or things like that. Is that what you mean?
Well, I mean, once you take light from the sun and make, with a solar cell, you make current, it's direct current. So all of our tools use alternating current because of the efficiency of alternating current transmission systems. So if you use a solar cell in your home, you got to power the electrical circuits, the refrigerator, the stove, maybe, all your lighting systems, and they're designed for AC circuits. So you have to convert direct current to alternating current, and those electronic conversion circuits currently are made of silicon, but they're not the most efficient. The materials we're making today for LEDs can be used to replace silicon with a much higher energy conversion efficiency. So there will be a day when power supplies, like are in your laptop, your cell phone, your refrigerator, your air conditioning system, they're all based on non-silicon semiconductors like the ones we're using for LEDs. So I think it's an interesting, if you will, spin out technology that all the work we put into making light-emitting diodes with very high efficiency now can be transferred to making power supplies with very high efficiency. And we can drive them with high efficiency. We'll see a day, I think, not too long, when everyone who understands power supplies and power distribution will know that these materials have come to the commercial market and have dominated the commercial market for high efficiency usage.
I know that you helped develop thin film technology that was necessary to make these semiconductors that are going into LEDs. And you even mentioned doing some work with Professor Holoniak at Rockwell, all of that in your past. So what was your first, I guess, exposure to developing LED technology?
Well, actually, when I was an undergraduate at the University of Illinois, I had a senior level class with Professor Holoniak, and he was a very dynamic lecturer, had a lot of interesting ideas to share with us. And he one day brought a sample of an LED to class, one of his early LEDs, and he put it in a dewar of liquid nitrogen that cooled this device, and suddenly the whole dewar lit up with bright red-orange light. So what was a sort of faint red speck became this gigantic light source that sort of lit up the region around this dewar. So it became quite interesting to me to what was going on in the physics of that. And fortunately, I was able to take a second class from him and learn more about this. And then when I decided to go to graduate school, I asked him if I could join his group. And fortunately for me, he said yes. And so I joined his group. So I did my PhD, my master's and my PhD work with him. And our whole group was working on light emitters, mostly on visible light emitters. We actually made the first high efficiency yellow light emitters, but they were rather crude devices. And it took a lot of work to commercialize that, which George Crawford, who is one of the other winners, one of Nick's students actually, developed when he was at Hewlett Packard. So I've been working in LEDs since 1970, directly or indirectly.
Wow.
And when I left Illinois with my PhD, I went to Texas Instruments in Richardson just outside of Dallas, and worked on gallium phosphide green LEDs. So my first job was LEDs. And I left Texas Instruments in 1975 and went to Rockwell International in Anaheim, California, to work on this process that we use today for growing these thin layers. Harold Manasevit, who's a chemist at Rockwell International, had developed a process in 1968 for growing semiconductor thin films that was somewhat distinct from other technologies in the research space. And I came there to try to develop it and understand it and push it farther. So it took me a while to scrounge a bunch of used valves and tubing and all sorts of pieces and parts to build a system, a reactor, as we called it, to build a way to make these thin layers. So it took a while to build this system. It took me about 5 months of working alone late at night, during the day, bending tubing, designing this layout, electronics, switching valves, and so forth. And once I had that, I started to grow films, and became clear that we could make really nice, smooth, thin films. What was missing was how good are they electrically and how good are they optically. So I did some studies of that and made first a solar cell, actually made the first solar cell using this process. And that worked. So I said, well, let's make some light-emitting devices. And I was always interested in laser diodes because of Nick's work on laser diodes and our research at Illinois on lasers. So we worked on semiconductor laser diodes, and I made the first semiconductor laser diodes using this process in 1977. And that became such a turning point for the technology that a lot of people started to work on this process and use it. And from there on, probably by the early 80s, a lot of companies had started to develop it for various materials. And especially in Japan, they worked on it for red and yellow LEDs, and so did Hewlett Packard, George Crawford's group. So by 1986 or so, there was a lot of interest in this, sort of 10 years after my first laser diode and my first solar cell. We call this process MOCVD. It stands for metal organic chemical vapor deposition. So today there are literally thousands of large-scale MOCVD commercial reactors producing LEDs throughout the world, and square meters of epitaxial films being grown every day to make billions of LEDs.
Wow. Did you have an idea back then when you were even in grad school or at Rockwell that metal organic chemical vapor deposition, that was going to be a big commercial, I don't know, blockbuster, if that's the right word?
Well, I had the feeling that this process, which has some unique characteristics, one of them being it could handle the element aluminum very conveniently. And aluminum is an important column 3 element in all of our semiconductors for LEDs and other devices, laser diodes, as well as LEDs, and even transistors. But the fact that we could use aluminum in a chemical form, turns out a liquid form, and grow semiconductors with aluminum atoms contained in the film was a big advance. Up until that time, no one had a process demonstrated for that to produce high quality material that was vapor phase. The vapor phase aspect allows us to, at least conceptually, grow very uniform films over large areas. So once I had this first laser diode, I actually demonstrated I could grow it on a large substrate at the time, which was about 2 centimeters on a side.
Hmm.
That was a large
Yeah.
substrate. That
Yeah.
was an incredibly large substrate at that time.
Yeah.
And I think in actually my first paper I published, I speculated that this process could be scaled to over 200 square inches per run. So I right then had the idea that this was going to scale, and however, it was off by like an order of magnitude in the area. There are much larger areas now per run, 6 to 8 inch wafers in a single run. So you can imagine 8 inch wafers of LEDs coming out of this
Yeah.
reactor every 4 or 5 hours. Nevertheless, that took a while to happen. It took a long time for commercial reactor designers to get involved and start marketing products that could make uniform layers on multiple substrates. Substrate area has moved from nominally 2 inch diameter, which was my first reactor, to 12 inch, multiple 12 inch wafers per run. In a similar technology development to silicon, actually, the area per run has increased and the throughput has increased as well. So efficiency of source use is important because it's expensive to grow these materials. So you want to have the maximum use of your chemicals and not have a lot of it left over or thrown away in some sense.
Mm-hmm.
But I think it was pretty obvious from, in my view, from the first work I was doing that this handled aluminum and it could be scaled and it was going to become the dominant materials technology. It has become the dominant materials technology for these wide band gap LED materials, for high power electronics, for high frequency electronics, for solar cells. So if you go to the space station today, you'll find LED lighting there for the astronauts, but you also find outside big arrays of solar cells. All those solar cells are made by MOCVD. And so any near Earth orbit satellite today uses solar cells made by MOCVD. So you're talking about SpaceX and their constellation, their building of direct communication satellites. That's all powered by MOCVD solar cells. So this technology has not only changed a lot of things about what we're doing here on Earth, it's changed a lot of things of what we're doing in space. And one thing we pointed out to people is that not only are LEDs good for lighting your home, they're good for lighting your plants. So people are now growing indoor agriculture, I call it artificial agriculture, where we no longer need the sun. We have optimized LEDs that couple directly to the photosynthesis chemical processes of the plants. And so the energy efficiency of producing food can be increased. Especially important if you're in space, where there is hardly any sun, or on Mars, where there's hardly any sunlight, very weak flux of photons from the sun. You're going to need LED lighting to grow your potatoes, as Mr. Damon showed us in The Martian.
Yeah.
So I think it's going to end up being in outer space too, not just on Earth. It'll be used in the trip to Mars and back. It'll be used in any moon bases. Obviously, we're not going to fly a whole satellite full of potatoes to Mars. We're going to have to grow food there largely. We got to find water. We got to find the right soil. There's a whole chemistry of food production we need to reinvent for Mars, I suppose, if you're going to live there any length of time. I think this process touches beyond the Earth, if you will.
Yeah, it definitely has huge potential. It already reached a huge potential here on Earth. And it makes me think of the MOCVD process that you did a lot of work on specifically. I know that helps you make really thin films, you were saying. Why are thin films from that process so critical for making LEDs or other similar electronics?
Well, without getting involved in quantum mechanics too much, it turns out that in the way we design semiconductors today, a lot of the useful part of our designs can be realized efficiently in thin layers. So in the case of LED, your goal is to take electrons that come from the power supply and recombine them in such a way inside the semiconductor that they emit photons. So this energy conversion process where we take an electron at high energy, take some of the energy away in terms of a photon, the electron continues on in the circuit and goes back to the battery or power supply and it comes around again. It's sort of like pumping up water out of a well. You pump it up and it flows down. That process of light emission is more efficient if you can confine this electron spatially in a certain region of the device where it changes from positive type conduction, we call p-type, to negative type conduction, we call n-type. So an LED is basically a p-n junction, p-n being positive and negative. And if you confine electrons to that small, tiny region where the material changes from positive to negative, you can make a very efficient light emitter. And so thin films become part of that design space. Similar things happen for transistors. We're used to silicon transistors. No one thinks too much about them, but the whole design of a silicon transistor these days is at the quantum level. It's literally at the sort of nanometer scale. And again, thin layers are part of that whole design space. So whether we're talking about light emission, laser diodes, high-speed electronics, they're all involved in very thin layers in one form or another. A solar cell is a little different type of design, but there are thin layers in the solar cell as well, because it turns out today, if you would ask Elon Musk about his solar cells, he'll tell you they are 3-junction solar cells, or maybe 4, depend on what he's using, but probably at least 3 junctions. So it's a stack of 3 p-n junctions stacked one on top of the other. It sounds bizarre, but it turns out that's important to get high efficiency. And between each of these p-n junctions, there's a very, very thin layer that allows current to flow across the interface.
Mm-hmm.
Again, critical part of the device design is this thin layer. So Mr. Musk, who's a very clever man, knows all about his solar cells, I'm sure, and would tell you, yes, that's a critical thing. I have to have thin layers in my solar cells. So it's actually a technology that, again, MOCVD is powerful to achieve. It's used for all of these devices because of its efficiency, its cost effectiveness, the quality of the material, the control you can achieve. And we're fortunate that Dr. Manasevit thought of this process long ago in 1967 and published his first paper in 68. Manasevit was a chemist, so he was not that interested in the electronics and devices and all that. So that's where I took it over, if you will, and developed it for that purpose and showed it could be used for that purpose, which a lot of people didn't think was true.
So you pretty much clarify something I was wondering, because I know you come from an electrical engineering background originally, but you work with chemists. I assume this was really interdisciplinary. Did you have to work with other sciences and engineers to really develop LED technology?
Sure. These technologies build on so many different disciplines. One primary example is physics, of course. Physics is the basic tool set we use for semiconductor analysis and characterization and understanding devices. quantum mechanics, critically important development that occurred around 1940 for solid state materials. Another discipline of engineering that we use a lot is chemical engineering, because these are all very chemical intensive processes, whether you're talking about MOCVD, the growth process, or the device processing processes. So once you have your 12-inch diameter epitaxial wafer, you have to make LEDs out of that. And so it's not quite as easy as cutting a loaf of bread and making sandwiches. There's a lot of things that have to be just right, a lot of chemistry that has to be just right to do that efficiently. So chemical engineering, chemistry, physics, electrical engineering, those are all really underpinning ideas and knowledge that is the basis of LEDs today.
And I have a language question as well, not to get too into the weeds, but I understand that MOCVD sometimes is referred to as metal organic vapor phase epitaxy. And that sounds very jargony as well. Is there a reason to use one phrase or another? Is that accurate that they're the same thing?
Well, here's what I understand from talking with Dr. Manasevit when he first developed this process. He was looking for a process that could deposit films of all kinds, not just epitaxial films. So he had the big picture in mind, and so his version of this name came from two aspects. One is, at the time he was doing this, he was trained to be a metal organic chemist. He got his PhD in organic chemistry using metal organic compounds. At the time of this work, the chemists referred to this whole field as metal organic chemistry. As time went on, they changed it to organometallic chemistry. So they put the organo part first and the metallic part second. But Manasevit was interested in the metal part, right? And so metal organic came first. He wanted the metal. He didn't care about the organic. That's just exhaust rubbish that he doesn't need. Other chemists like the organic part, so they're thinking more about organic. So there are two versions of this name: metal organic and organometallic. So you can talk about MOCVD or OMCVD. So you'll see both. Then there's the issue that I brought up. Manasevit wanted to consider this a universal deposition technology. Epitaxial films, polycrystalline films, amorphous films, whatever you need, I got it here. One size fits all. When people started to grow semiconductors, they wanted to make epitaxial layers. So a subgroup of the practitioners of the art decided they were going to change the name to VPE, vapor phase epitaxy. So you have actually four names for this technology, depending on where you came from.
Okay.
And my view is Hal had it right. Manasevit had it right. Why change the name? It's like suddenly someone says, oh, I don't like the word sun. Let's change it to balloon. What did you learn by changing the name to balloon? Well, it's round and it's yellow. It's like a yellow balloon. Well, you didn't learn anything by changing the name. So again, it depends on where you come, almost which country you come from, because the tendency was to adopt one or the other of these different options. But I think today it's almost universally called by MOCVD. Mm-hmm. It's, if you Google it, you'll find all of this technology, and a lot of people in China, in Singapore, in Taiwan, in Japan, in Russia, in the European countries, in the United States, and Canada, all using MOCVD. But other places will still use those other versions. Again, it's the same thing, the way we practice it today. Same chemicals, same goal. But Manasevit had a bigger picture in mind when he chose his name.
Thanks for clearing that up. No, that is helpful for me. And I wanted to ask you a little bit more about your pathway to all this engineering. You already mentioned that you studied engineering at the University of Illinois at Urbana-Champaign. A lot of people know UIUC has that reputation of being one of those top tier hard engineering schools. I'm just curious, what was studying engineering like when you first went through it? Was it hard? Was it easy? Were you the type of person to just know exactly what to do all the time? Or I'm curious.
Well, I'm from a farm in Illinois. It's only 80 miles south of Chicago, but the township that I was raised in, where our farm is just basically farms. There's no village, there's no town, it's just farms. The whole township is farms. So we went to school to the township nearby, and it was a very small high school. My graduating class had 36 people in it.
Hmm.
And remember, this is a baby boomer time. So this is after World War II, the baby booms had come along. And one of those 36 was my twin brother. So, that,
Oh,
that was even smaller subset of
wow.
people. And then my brother and I both applied to the University of Illinois and got admitted. My brother was a veterinary medicine student. He's a veterinarian in Illinois now. And so we moved from high school with 36 in our graduating class to 36,000 in Champaign-Urbana.
Yeah.
So you can imagine the sort of quasi-shock being raised on a farm in a small farming community with the town where we went to school had 650 people in it. Fortunately, we were both good in our classes, and so I got admitted to Illinois, and so did my brother, and we plugged ourselves in and got busy and worked hard. So I was fortunate to choose electrical engineering, sort of accidentally, actually.
Oh, really?
I was interested in physics and math and chemistry, but one of my cousins had a friend who was going to University of Illinois in electrical engineering. So he was several years older than I was, and so I talked to him, and he told me some of the things he was learning, and I thought, well, that sounds nice, sounds interesting, and so I applied to Double E and got admitted, and so I was lucky,
Wow.
if you will, to randomly walk into electrical engineering, and then randomly walk, if you will, into Nick Holonyak's classroom and discover this whole new world that he was describing to us.
Huh.
And lucky enough to be part of his team for 3 years and then to be able to develop this MLCVD technology that's now taken over, if you will.
Yeah.
We talk about compound semiconductors, production-wise, it's almost all MLCVD, certainly for LEDs, for mostly lasers, for most of the high-frequency electronics. Today everyone is thinking about driverless cars and self-driving vehicles, and
Yeah.
we're all actually hoping that happens soon. We just had a 100-car pileup outside of Fort Worth, as you know, and if those were self-driving cars, there would have been no accident. No one would have gotten hurt. No one would have gotten killed. There would be no fender benders because the cars are communicating with each other. They're constantly scanning their environment, and all of that would not happen. So at some point, this whole technology we're talking about, MOCVD, light-emitting diodes, laser diodes, sensors, are going to be in those vehicles, and it's going to save a lot of energy in terms of transportation power. It's going to save a lot of lives, and people won't be run over by cars at night or have accidents when they fall asleep, hopefully. And these kind of snowbound, icebound accidents won't happen either because the car is going to know it's icy out and probably won't let you go fast. Won't let you move along at 30 miles an hour. You got to move at 3 or less, right? So it'll be interesting to see this transition. I think the world is not only going to save energy, but they're going to save lives using this technology. And of course, it already saves lives in many ways. I know, for example, even in the 10 years ago or longer, this LED technology had been brought into Sri Lanka and Ceylon and remote parts of India where they don't have convenient electrical service. And so people use gas, propane, lighting, and that caused fires and people died. And now you can use a simple solar cell outside during the day and a battery and light your home at night so that children can study, people can cook, people can even watch TV with their battery powered devices, charge their cell phones. So even that, while it's a small scale in terms of energy, it's a big effect in terms of number of people who benefited from it. Just having LED lighting with a local solar power system to power your lighting at night. Same thing's true for fishing boats, right? They need power on fishing boats and for lighting and things, and for people to do their homework, to do their business, to do shopping, to
Yeah.
do cooking.
I'm glad you started talking about these modern uses of LEDs, and it sounded like you had ideas for the future in terms of safety and space. Is there more work that has to be done to improve LED technology to achieve all these things?
Well, we have before us a great array of people working on this problem. But yes, there is more efficiency we can probably achieve in solid state lighting, especially in the green spectral region, because those materials are not as well developed as, for example, for blue. And green is obviously important for a lot of things, but at this point, I would say the biggest improvement that's needed is in the ultraviolet and in the non-visible light emitting diodes, where we can use them to, for example, sanitize surfaces, sanitize water, sanitize air. The COVID crisis has brought forward the fact that our environment is one of our enemies in terms of how we use it and how it's a fertile spreading vehicle for viruses. And as people get closer together, the population increases, the transportation opportunities increase. In 1918, when we had the influenza deaths, people weren't traveling by air, moving around the country. You had to get on a train or a horse to move around the country. And so having your environment safe is a critical feature of the new COVID world. Of course, it hasn't been suddenly we have a problem. We've had a problem, but it hasn't been addressed well because of the cost. If we can bring the cost down for UV lighting from LEDs at the right performance, we can purify air inside every building and inside every school. We can purify the water in every person's home water supply. We can purify surfaces that might be exposed. During this COVID crisis, I bought a little UV LED driven case for my iPhone, and you put your iPhone in the case, close the lid, the UV LEDs turn on, and it kills all the viruses on your iPhone.
Whoa, what? That's interesting.
It's called phone soap. Phone soap. And phone soap basically uses light to deactivate any pathogens on your phone.
But they're not UV LEDs, I guess.
They are UV LEDs. They're
they are? Okay, expensive.
Well, they're low power. We need to get to the level of high power to get to the commercial industrial scale application. So if you go to any water plant in any civilized city in the world, you'll find ultraviolet lamps killing bacteria in the water. Those ultraviolet lamps are not efficient. They're old-fashioned, similar to the fluorescent lighting we use in our classrooms right now. And if we replace those with LEDs that are efficient, again, power energy saving is going to happen. Replacement costs go to nearly zero because the reliability is so good. So again, you have a big win in terms of safe water, safe air, safe surfaces. If you had, for example, in school, there's a certain wavelength of light that will kill bacteria, but humans are not sensitive to it. It doesn't cause skin cancer. It doesn't impact your retina. So you could have a floodlight of this wavelength in your schoolroom, and it would kill any pathogen that's on the children's desk or books or pencils potentially. So these are new application spaces where if everything goes well, and we have a lot of smart people working on this, so I think it's going to happen, and a lot of market pull, we're going to find that MOCVD, UV LEDs are everywhere as well, and people will be healthier and safer for it.
If a young person today is interested in solving some of these problems or is interested in MOCVD, UV LEDs, all that stuff, what would you recommend they study or work on to try to go on this path? Do they have to study electrical engineering?
Well, as I mentioned, there are several disciplines that provide inputs to this technology. Electrical engineering is one, primary one, I would say, but underpinning that is chemistry and physics. And then there are the sister engineering disciplines like chemical engineering, industrial engineering, mechanical engineering. A lot of our tools that are used for this semiconductor-related processing are critically designed by really good mechanical engineers who understand how things work. Chemical engineers who understand the chemical processes that are involved. So there's several vectors, if you would, to get, or pathways to get into a contributory role so you can make an impact. Obviously, the basic idea is understanding mathematics, physics, chemistry, and from there you can build the other parts of this knowledge base that you need to design the tools, design the devices, to design the products that are going to be needed for people to conveniently use these materials and devices in their homes and in their lives, businesses and communities.
Thinking back to where you came from in Illinois, to all the different achievements you've had so far, I'm sure you've traveled all around the world. Do you have any last advice, I guess, for people learning engineering today? Is there anything you might have done differently or something you wish you could do today that you would urge other students or young people to pursue?
Well, I have just one comment about that. When I was in electrical engineering at Illinois in graduate school, because of what we were doing in Nick's laboratory, I decided I should take a chemistry class in physical chemistry. And so I did that, and I think it helped a lot. So I would say be open about where you're going to poke around in this general field. Take a chance. Take a walk on the wild side. Take a little walk off the pathway and see. I took a lot of math classes, complex variables, and those kind of things, because you never know what you're going to discover. That's a lot of poetry about that. Leave the path and discover something. And so take a few chances. Of course, you can't spend all your time wandering in the flower patch. You've got to eventually go back and start producing something, start focusing on the core you need to get a job, in quotes, to make an impact. So be open to other ideas. Dr. Crawford, who's one of our winners, as you know, got his PhD in physics, but he did his PhD work in Nick's laboratory as an electrical engineer. And then when he went to Monsanto to work on LEDs, he had this incredible background that was almost custom made for this kind of work. So be flexible, be open. Most importantly, find something you're excited about, because after working on this problem, if you will, for 50 years, if you're not excited about it, it's not going to work out well for you. I'm reminded by some very famous quotes of people who are some of my idols, but one of them was to work hard, because the people who are competing with you are smarter than you and are working harder than you. So you can never quite be the best in every aspect. So if you're not pushing yourself, there's other people going to be there first. And in this field, I'm going to say competition is useful. It's part of the way humans have advanced their societal situation. Obviously, wars are not good, but competition, friendly competition, is good. It drives us forward. Most of us like to succeed if we're playing a board game even, let alone trying to bring an idea to a commercial product that changes people's lives. And fortunately, I was involved in some of that kind of work that changed people's lives. It took a lot of work. I say there were long nights building things by hand. Fortunately, as a farm boy, I was used to building things by hand and working long hours. So that's part of it, is being devoted to your ideas.
Thank you to Dr. Russ Dupuis, electrical engineer, co-inventor of LEDs, and co-winner of the Queen Elizabeth Prize for Engineering this year. The K-12 Engineering Education Podcast is sponsored by my creative studio, Pios Labs, in Austin, Texas, where I work on several projects in engineering and education, like podcasts, educational technology, professional development, STEM curricula, and more. Follow Pios Labs on social media for latest news. That's PIOSLABS. This podcast is possible thanks to brilliant people donating to the show on Patreon each month. Help me continue the podcast. Donate to the show at patreon.com/PiosLabs and get some perks when you do. Visit the podcast website for show notes, links, transcripts, and more. Go online to k12engineering.net. That's K12 engineering.net. Thanks for your support, listener. Especially with all the crazy that's happening, I'm grateful you're still into hearing about engineering and education with me. So, listener, until next time.